Somewhere in the dark between the stars, a 47-year-old spacecraft is listening. Not for signals from Earth, not for instructions from engineers. It's listening to the interstellar medium itself, the near vacuum of gas and plasma that fills the space between star systems. And since 2017, it has been picking up something that wasn't supposed to be there. A faint, continuous hum. Not a burst, not a ping. A hum. Monotone, persistent, unwavering. Like the galaxy itself has a heartbeat. And Voyager 1 just pressed its ear against the wall and heard it for the first time. In May 2021, a team of astronomers led by Cornell University published a paper in Nature Astronomy announcing one of the quietest, and in many ways, most profound, discoveries in the history of space exploration. Voyager 1's plasma wave system had detected a class of very weak, narrowband plasma wave emission that persisted continuously across more than 10 astronomical units of interstellar space. In plain English, the spacecraft had detected the background sound of interstellar gas, and what that hum is telling us about the density, turbulence, and structure of the medium outside our solar system is making scientists deeply uneasy, not because the discovery is catastrophic, but because it reveals how much more complicated the environment out there is than we ever assumed. To appreciate why the hum matters so much, you first need to understand how scientists were measuring interstellar plasma before it was discovered. Since Voyager 1 crossed the heliopause in 2012, its plasma wave system, a pair of 10-meter antennas extending behind the spacecraft like rabbit ears, had been the only instrument in human history capable of directly measuring the electron density of the interstellar medium. But it could only do so during very specific events. Plasma oscillation episodes triggered when solar eruptions sent massive shockwaves propagating outward from the Sun through the heliosphere and into interstellar space. Here's how it worked. When one of those solar shockwaves passed over Voyager 1, it caused the electrons in the surrounding interstellar plasma to vibrate, to oscillate at a specific frequency that depends on how densely packed those electrons are. The denser the plasma, the higher the frequency of that oscillation. By measuring the pitch of that vibration, scientists could calculate the local electron density of interstellar space. The system worked, but it had a critical limitation. It was entirely dependent on solar activity. If the Sun wasn't erupting, Voyager wasn't measuring. Scientists were getting intermittent snapshots, sharp, reliable data points, but only about once a year, when a suitably large solar outburst happened to propagate all the way out to where Voyager was. The map of interstellar plasma density that resulted was, in the words of Stella Ocker, the Cornell astronomer who led the 2021 study, kind of sparse. James Cordes, the senior author of the study, and a professor of astronomy at Cornell, described the situation with a vivid analogy. Measuring interstellar space only during solar outbursts, he said, is like trying to study rainfall by only paying attention during lightning storms. You learn something every time the lightning flashes, but in between the storms, you're blind to the gentle, constant rain that's always falling. And as it turned out, that rain was the story all along. Stella Ocker set out to find a better way. She began filtering through Voyager 1's raw, plasma wave system data, looking not for the dramatic spikes of solar-triggered oscillations, but for something far weaker, something almost buried in the noise, and she found it. Starting in mid-2017, there was a signal. Faint, steady, nearly monotone. A narrowband emission, concentrated in a very specific, very narrow range of frequencies, that persisted continuously, without any solar trigger, across month after month of data. It was still there a year later. 2 years later, right up to the end of the dataset she was analyzing in early 2020. In over 3 years of data, the hum never stopped. Ocker described what she found in terms that were carefully precise and quietly astonishing at the same time. The signal, she said, is very faint and monotone, because it is in a narrow frequency bandwidth. But it is unambiguously there, tracking the interstellar medium continuously, without needing a solar event to trigger it. Voyager 1, she said, is saying, here is the density I'm swimming through right now. And here it is now. And here it is now. And here it is now. For the first time, scientists had a running, real-time, continuous measurement of the plasma density of interstellar space. Not snapshots. A movie. What produces this hum? The short, honest answer is, we're not completely sure yet. The leading candidates are thermally excited plasma oscillations, essentially, the random thermal motion of electrons generating faint electromagnetic waves, or something called quasi-thermal noise, a well-known phenomenon observed around other spacecraft in the solar system. Either way, the signal appears to track the local plasma density closely, rising and falling with it, in ways that are consistent and predictable. Ocker noted that its behavior before and after a known solar oscillation event in 2017 was highly suggestive that the emission's frequency traces the plasma density directly. It's a natural tuning fork, the medium itself, resonating at its own characteristic pitch. And that pitch is shifting. The most immediate scientific gift of the hum is the data it provides about turbulence in the interstellar medium, Previous measurements, taken only during solar oscillation events, suggested that the very local interstellar medium, the region just outside our heliosphere, has a large-scale density gradient. In other words, it gets denser the further Voyager travels from the heliopause. But those measurements were so sparse that scientists couldn't see the fine structure. They couldn't see what was happening between the data points. With the persistent hum providing a nearly continuous readout, Ocker's team could, for the first time, map the density fluctuations at scales of roughly 1 astronomical unit, the distance from the Earth to the Sun, over a stretch of about 10 AU of interstellar space. What they found is that the interstellar medium is not smooth. It's not a uniform cloud of gas through which Voyager is drifting at constant density. It's turbulent. There are density fluctuations at multiple scales, regions slightly denser, regions slightly thinner, interwoven with one another in complex patterns. The team calls these off-scale density fluctuations that trace interstellar turbulence. And interstellar turbulence matters, because it affects how cosmic rays travel through the galaxy, how radio signals from distant pulsars propagate to Earth, how star formation occurs in molecular clouds, and how any future spacecraft we send into interstellar space will navigate an environment that is more variable and more active than we thought. The interstellar medium is not a void, it's a weather system. And we just got our first continuous weather report. And now for the part that is genuinely making scientists uneasy. The hum isn't just steady, it's telling a story about change. Based on the frequency of the persistent emission, Ocker's team was able to track how the electron density around Voyager 1 has evolved over time. What they found is striking. Electron density around Voyager 1 started rising in 2013, shortly after the heliopause crossing, and by mid-2015 had reached a level approximately 40 times higher than the density inside the heliosphere. That 40-fold increase is consistent with what scientists expected at the heliopause crossing. But the story doesn't end there. The density hasn't stabilized. It has continued to show fluctuations, and, in some regions, continued to trend higher as Voyager moves deeper into interstellar space. This matters for a specific and practical reason. Our models of the interstellar medium, the theoretical frameworks we use to predict what's out there, were built from indirect observations made at a distance. Radio telescopes measuring how signals from pulsars scatter through interstellar gas. Spacecraft inside the heliosphere making indirect inferences about the environment outside. But Voyager 1 is now giving us the direct measurement, in situ, from inside the medium itself, and the direct measurement shows more structure, more turbulence, and in some respects a denser medium than the models anticipated. That gap between prediction and observation, modest in absolute terms, but real and consistent, is what is drawing scientific attention. Shami Chatterjee, the Cornell research scientist who co-authored the study, put it plainly: we've never had a chance to evaluate the interstellar medium this way before. Now that we can, we're finding it is more active than we thought. There's also a deeper implication. The density of the interstellar medium affects the shape of our heliosphere, the bubble that protects every planet in our solar system from the full force of galactic cosmic rays. A denser, more turbulent interstellar medium exerts more pressure on the outer heliosphere. It shapes the heliopause, influences the termination shock, and ultimately determines how much cosmic radiation reaches the inner solar system. We've established in previous episodes that the interstellar magnetic field is already stronger than predicted, pressing on the heliosphere harder than our models assumed. Now the density data from the hum is adding another layer of complexity. The environment outside our cosmic bubble is more dynamic, more variable, and pushes back harder than we realized. And right now, Voyager 1 is the only instrument we have that can measure it directly. Here's the practical dimension of this discovery that doesn't get discussed enough. Humanity is, at some point, going to want to send another spacecraft into interstellar space, one purpose-built for the interstellar medium, with modern instruments, better power systems, and faster travel. Several proposals for such a mission already exist, most notably the interstellar probe concept, studied by Johns Hopkins University Applied Physics Laboratory. These missions will need to be designed to operate in the interstellar medium, and to do that, engineers need to understand what that medium actually looks like. How dense is it? How turbulent? What are the electromagnetic conditions? What forces will act on the spacecraft's antenna, its electronics, its instruments? The answers Voyager 1's hum is providing are, in this context, engineering data as much as science data. The density map that Stella Ocker's work has begun to construct is the most complete picture of the very local interstellar medium that humanity has ever had. Every additional parsec of data that Voyager sends back before it falls silent adds to that map. And when the time comes to design a new interstellar probe, to decide how large its antennas need to be, how robust its plasma instruments should be, how to protect its electronics from a medium more electrically active than models assumed, the hum that Voyager 1 detected in 2017 will be part of the foundation for those decisions. A 47-year-old spacecraft, running on a few dozen watts of nuclear power, doing foundational engineering work for missions that haven't yet been funded, let alone built. Let's step back and appreciate what has actually happened here. a spacecraft launched in 1977 with 70 kilobytes of computer memory, less than a single text message, has given us the first continuous real-time measurement of the interstellar medium from inside it. A graduate student at Cornell, Stella Ocker, filtered through decades of barely above noise data and found a signal that nobody had deliberately designed a mission to find. And that signal, that quiet, monotone hum, is revealing that the space between the stars is not the silent, empty, well-understood void we imagined. It is turbulent, it is structured, it is denser and more complex than our models captured. And it is telling us something about the galaxy that we are only just beginning to learn how to hear. James Cordes said it beautifully. The interstellar medium is like a quiet or gentle rain. In the case of a solar outburst, it's like detecting a lightning burst in a thunderstorm. And then it's back to a gentle rain. For decades, we only knew how to study the lightning. Voyager 1 just taught us how to hear the rain. And the rain, it turns out, has been falling all along. Constant, patient, covering everything. In the dark between the stars. If this episode changed how you think about what lies beyond our solar system, subscribe, and leave a comment telling me what surprised you most. Every week we go deeper into the real science behind the Voyager missions. Next episode we cover what happens when Voyager 1 finally goes silent, what is irreplaceable about what it's doing right now, and why no other spacecraft can take its place. See you there.